So here we're going to introduce the optical properties of so-called biaxial minerals, and we're going to use this diagram from Dexter Perkins' online mineralogy textbook. So biaxial refers to the case where we have two separate optic axes, but we're going to get to that a little bit later. First, we want to talk about the axial directions themselves. We have the crystallographic axes A, B, and C, and this will be for any mineral that is in the orthorhombic, monoclinic, or triclinic mineral systems. So all of these systems here have the case where they have unequal A, B, and C axes. So these are of unequal length when we're measuring out, for example, distance to crystal faces or distance to atoms or atomic clusters. Well, with three distinct crystallographic axes, we also get three distinct axes, X, Y, and Z, for the transmission of light. Now, why do we use X, Y, and Z if we already have this notation here? Well, the reason why is X, Y, and Z might not correspond to the A, B, and C axes. As shown here, this is a case for this particular diagram of a monoclinic crystal. So for the orthorhombic case, X can be parallel to A, B, or C, but we never know which one. It could be parallel to A or B or C, and then Y could be parallel to any of the three, etc. For the monoclinic and triclinic systems, we're going to have these angles. The Z crystallographic direction will be parallel to B, but X and Y can switch places, and they will have some angle. They will not be parallel to A or C. And then for the triclinic system, everything's at a different angle. So we would have some angle between not just C and A between their respective optical axes, but also between the B axis and whatever optical axis. And again, this is drawn as Z, Y, and X, but these can be mixed around. So there's not always a one-to-one correspondence between these fellows here. So don't think about it in that way. So and this is why when you look in Dear Halley and Zussman, you'll see diagrams that show exactly this relationship. So you can see the relationship between Y and whatever it's closest to, A, B, or C, etc. Now, there are another couple of optical properties that are very important. For the uniaxial minerals, we had a single optic axis, a single OA, the way it's shown here in this diagram. And when you look down an optic axis, that means the mineral, when you look in that direction, it looks like it is isotropic. It's a special direction. When you look in this direction here, if you make this special cut perpendicular to that optic axis, then in that particular cut, it will appear as if all the rays are moving in the same velocity, and so it'll look like it's isotropic. But with uniaxial minerals, there was only one special direction, which is also coinciding with the C-axis. Here, we have two special directions. We have one optic axis shown here, and then for this case here, we have another direction where we can cut the material perpendicular to that direction, and when we look in that direction, all the rays will appear as if they're moving with the same velocity. So there are two ways you can look at the mineral, two directions you can look at, where the minerals will look isotropic. If you cut the mineral in any other random direction, then it will not look isotropic, and you'll see the various values that are associated with X, Y, and Z. And how would we notate them? Well, we notate them with the Greek letters alpha, beta, and gamma. So the n value along the x direction is here. We would call that the index of refraction would be n alpha. For the y direction, that would be n beta. And then for the z direction, that would be n gamma. And we have this case here where n alpha is not going to be equal to n beta, is not equal to n gamma. So when you look up an orthorhombic, monoclinic, or triclinic crystal in a book like Dear Halley and Zussman or some other optical mineralogy reference, you'll see three distinct values of the index of refraction that are listed that correspond to these X, Y, and Z directions. Now there's one final aspect for us to cover. If we have two optic axes instead of one, well, that first of all gives us our name here, biaxial. By biaxial, we mean that it has two optic axes, whereas the uniaxial mineral just had one. But it also means we could start thinking about the angle between those optic axes, which is shown here in another diagram Also in the online mineralogy textbook by Dexter Perkins, you can consider this one as being equal to V, and then this one over here is also an angle equal to V. Add them up and you get 2V. And so that is another optical property that you can look up for various minerals in the orthorhombic, monoclinic, and triclinic systems. All biaxial minerals will not only have a value for delta. Remember, delta is our birefringence, and we can take the maximum minimum values, and those will usually be gamma and alpha. We'll just take the absolute value. It doesn't matter which one is larger. Beta will usually be the intermediate fellow. So this will be our birefringence, just as we saw for the case of uniaxial minerals. But something that biaxial minerals have that uniaxial do not have is this 2V angle. And so this is the angle between the two optic axes, the two OA that are shown in this figure. Notice here that as the 2V approaches 0, then what happens? If the 2V is equal to 0, then we would have a uniaxial mineral. This guy would now be the same as this guy here as this angle disappears. So you can consider the uniaxial minerals to be a special case where the 2V is equal to 0, and then we would have minerals that are effectively in the hexagonal and tetragonal system. So we now have a third optic property compared to what we saw before. We have the indices of refraction, 3 of them instead of 1 for isotropic and 2 for uniaxial. We have the birefringence, just like we do for the uniaxial, where we take maximum and minimum values and we look at their difference. And then we have this third optic property, 2V. These are all things that we can identify in the microscope and look up in the textbook and use as a way to identify minerals using the petrographic microscope.